Okay, thank you very much. So I'd like to thank the organizers for organizing this event and for inviting me. So I'm going to talk today about some connections between a problem which comes from econometrics or applied statistics, which is rather popular, which is called the quantile regression problem, and the connection with this problem and optimal transport, which in fact enables us to generalize what is done in dimension 1 to higher dimension, okay? And in the first place, to extend, one way to extend the notion of quantile to several dimensions. And this is joint work with Victor Chernozhukov from MIT and Alfred Galichon, who's in the States now, but we're still officially in Sciences Po. I don't know, it changes quite fast. Okay, so what typically an econometrician or an applied statistician is interested in is to have a device, a way to model dependence between two variables, which I will denote by y and x. So y is a variable you want to explain, and x are explanatory variables. So the most standard problem you can think of is having a model for explaining a conditional mean by least squares, for instance. And in this talk, I'll be interested in something else, which may be more natural in some settings, for instance, in biometrics, which is instead of estimating a mean, you're interested in estimating a conditional quantile, let's say the median, for instance. Okay, and it has a lot of features and applications. Let's say in biometrics, if you're interested, for instance, why think of it as being variables capturing the health of a newborn baby, and X are things like does the mother smoke and things like this. This is typically settings in which you are more interested in extreme values rather than means, right? Okay. So what I'm going to do today is, well, if you don't care so too much, is my talks will be divided into two parts. I will recall what is done usually in one dimension, when y is univariate, it's 1D. And in the second part of my talk, I'll discuss a little bit how we can extend this kind of analysis to the multivariate setting by using ideas from optimal transport. Okay? So this is first part, quantile regression, old and new. Old and new is very fashionable expression when you're dealing with optimal transport stuff. So I'll say things about what is a quantile, conditional quantile, how it is related to some optimality principles, and then I'll go to the multivariate case. And of course, do not hesitate to interrupt me at any time if something isn't clear. Okay, so the notion, you're all familiar with the notion of quantiles. We've got a random variable y, one-dimensional. You look at its CDF, its cumulative distribution function f, and when you invert this function, which is typically increasing fy, when you invert it, you get the quantile function. So for instance, if you fix a level t when it is 1/2, this is the standard notion of a median, you can look at other values for t, which gives you percentiles and so on. And okay, so there are many more ways, in fact, to see this object, either for a fixed level t or globally as a function of t between 0 and 1 as an increasing function of t. So the first observation, which is very important in practice in the quantile regression device of Koenker and Bassett, I'll be clearer and more detailed later on, is to see that in fact the quantile at level t is the solution, is a solution. In fact, I'm not being precise here. You may have a not very regular distribution function, so there may be several quantiles. It's a solution of an L1 type minimization problem. The quantile at level t is in fact a minimizer of this functional. So you take the expectation of y minus alpha positive part plus something linear with a weight 1 minus t. And when you write down the optimality condition, you exactly get what you want. You prescribe the mass to the left and the mass to the right, right? Another way to see this is more in the framework, or more in the spirit of optimal transport, what is called polar factorization in some sense, is to say that this quantile function, qi, is characterized by the fact that you can write pointwise your random variable y as qi of u for some random variable u, which is uniformly distributed, okay? And this random variable u, okay, is actually among uniformly distributed random variable, the one which is maximally correlated to your signal y, okay? So we see that, and we'll always in this talk play between those two ways of looking at quantiles, either locally, t by t. So for instance, the formula which gives you the quantile at level t by inverting the distribution function is typically a t by t approach. The variational problem we saw before is also for a given t, or a more global approach in which you look for a pointwise relation y equals q of u, where the law of u is prescribed. Let's say you normalize it to be uniform, and q is non-decreasing. Okay? Fine. So let's go now to the conditional setting, where on top of our problems, we have another variable, x. It may be multivariate, take values in Rn. And we look now at the conditional CDF. F of xy is the probability of y being less than y given the level of x. And we're going to invert this in some generalized sense for fixed value of x. So it gives you a function of x and t. T is, again, something between 0 and 1, a level of probability. And you inverse with respect to the second variable. So you get something which is non-decreasing with respect to the second variable. Okay? So when you do that, let me skip the assumptions are not essential for the moment. So I'm assuming some sort of regularity just to make the exposition simpler. So I assume that the joint law of x and y has some regularity. In the first place, I assume that it gives no mass to hyperplanes, things like this. This is important for quantile regression. And okay, so you've got this f of xy, and you've got the conditional quantile function q of xt. So when you do that, you can define another random variable, u, which is f of x and y, okay? Where f, again, is CDF with respect to y conditional on x. And when you look at the distribution, the conditional distribution of this u, the probability of u is less than some threshold given x. It's exactly, by the very definition of quantiles, it's exactly t. Okay, so it does not depend on x, and it's the distribution of a uniform variable. So what you get here is that this random variable u is uniformly distributed, and it's independent from x. Okay, and you've got also a pointwise relation. You can invert u is f of xy. It means exactly that, well, ignoring degeneracy situation, or it gives you a pointwise relation. U is q of x and u. So the conditional quantile does this job. It expresses pointwise y as a function of x and u, where u is uniformly distributed, independent from x, and the q is increasing in its second argument. So there's also, of course, also a variational principle behind this, which is that this function u, this random variable u, which is uniformly distributed, is in fact solving some optimal transport-like problem, which goes like this. It is maximally correlated to y among random variables, which are not only uniform, but which are also independent from x. Okay? So what we are doing, and it's a sort of variance of the optimal transport problem. So here you see what we are doing with conditional quantiles is a sort of conditional polar factorization. You write y as a function of x and u, which u is, the law is prescribed, it's uniform, say. It's independent from x, and the function q is non-decreasing with respect to its second argument. Okay? So how do you do things like this in practice? So in practice, what you want to estimate this function q of x, right? So what Koenker and Bassett did in the late 70s is that they designed a regression scheme to estimate. You postulate a linear form for the conditional quantile, and they devised a variational scheme to estimate the coefficient in this regression. Okay. So okay, that's what we are going to do now. So to fix ideas, let's take x to be centered. not really important, so the mean is 0. And I will denote by m the law of x. I'm going to make a few assumptions on the regularity of this law, but this is not so important here. And okay, quantile regression is specified when the conditional quantile as a function of the explanatory variable x is in fact linear. So it means you have got two functions, alpha and beta, such that the conditional quantile is alpha t plus x beta t. And it has to be consistent with the property of quantiles, which is monotonic. So this function, as a function of t, should be non-decreasing. Okay? So this is quite demanding, but this is the underlying assumption of what is done by econometricians when they perform quantile regression. So we say that quantile regression is specified if the joint law has this property that the conditional quantile is in fact linear with respect to the explanatory variables. So in this case, when you look at the random variable point of view, it exactly means that you can write y as alpha u plus x beta u, where u is uniform, independent from x, and that's it. And it's an interpretation as a linear regression, but with a stochastic factor. U is a sort of latent variable, okay? The interpretation of this pointwise relation is quite clear in terms of linear regression. Okay. So now it may be very demanding, and how do we estimate a relation like this? How do people do in practice? They use a similar optimization principle as the one I described in the beginning, which is the following. So you want to estimate, you fix a level t, okay, for your latent variable u, and you obtain the regression coefficient alpha and beta by minimizing this convex function. Okay, it's a bit degenerate. It's more like a linear-like behavior. This is a convex programming problem. Of course, it's not very difficult to see that if the model is specified, if the true quantile is in fact linear, you will estimate the correct values by this optimization problem. And there's a nice, in fact, it's a very simple problem. It's convex programming. It's even linear programming in some sense. And it has a dual formulation which goes like this. So how do you solve this problem? You introduce a dual where you look basically for a random variable ut, t is fixed. You fix the mean, you fix the correlation with x being 0, and you want ut to be maximally correlated to y. When you do that, it's not very difficult, at least at the formal level. You add a multiplier, a Lagrange multiplier with this constraint. This is the alpha. A Lagrange multiplier with this constraint, which is a vector beta, which is the same dimension as x. And the optimality condition or complementary slackness for this convex duality, to convex problem with duality, is just to say that ut should be 1 exactly when y is above, strictly above this linear form, this linear function of x, and should be 0 when y is strictly below. And you fix the multipliers exactly so as that those conditions are satisfied. Okay? So typically, of course, there's a little bit of indeterminacy in case where you have the joint law of x and y might give mass to the hyperplane y equals alpha plus beta x, but I'm ruling this case out for the purpose of simplicity in this talk. Okay? So the problem is quite clear. The ut is uniquely defined if I'm assuming that the joint law of x and y does not give mass to hyperplanes, and it's the characteristic function of this half space where the alpha and beta are just are obtained such as that both conditions are obtained. And numerically, it's not very difficult to solve a problem like this. Okay, so now, okay, you are asking yourself, this is fine if the model, the true joint law is specified, you're estimating correctly the coefficient on your regression, and now you ask yourself, what is this variational problem doing in the general case, in the case where you have no reason to believe that the quantile should be linear with respect to x. Okay? So this is what I'm going to do now. So let me denote that alpha QR, beta QR, and UT QR, what you estimate by solving the two optimization problems we had before, so by performing in practice the quantile regression. And I will say that quantile regression is quasi-specified if what you do in practice is consistent with monotonicity of quantiles, which is, okay, I will say that quantile regression is quasi-specified is what you do by solving those optimization problems as a good monotonicity property, okay? And when you play a little bit with this, with those conditions, what you discovered is the following, actually. If quantile regression is quasi-specified, you integrate with respect to t the UTQR we had before, okay? Then in fact, it's a uniformly distributed random variable. It's not true anymore in general that it is independent from x, but x is mean independent from this UQR, meaning that the conditional expectation of x given this UQR is 0. And you've got a pointwise relation. Y is still a linear function of x, where the coefficients only depend on this UQR. What you lose from, you lose very little from the specified case. What you lose is just the fact that u is not independent really from x. You have to weaken this condition to the mean independence condition. And what's not difficult to see also is that this u we've got here solves a problem which should be familiar to you. It looks a little bit like a martingale optimal transport problem in some sense. This u maximizes the correlation with the y among random variables for which the law is prescribed. Again, it's uniform on 0, 1, but which is such that x explanatory variables are mean independent from the u. Okay? So from this variational point of view, you see a couple of things. So first of all, there is uniqueness in this decomposition. If y can be written as a linear function, an affine function of x with random coefficients with a u which is such that x is mean independent from u, in fact, a decomposition like this is unique. And that's it. I mean, there's not much more to say. So now we see that there is a range of decomposition of y given x. The first one is a general, with a general quantile. Okay, you write y as a non-increasing function of u with u independent from x. And what the underlying idea behind quantile regression is you strengthen the form of the dependence. It's linear, but you slightly weaken the independence of u and x. Okay. So now the question you may ask yourself is that, fine, I've weakened a little bit the quantile specification assumption. What does this device of Koenker and Bassett does in the general case? Okay, and can you extend in higher dimension? So, okay, general case is you cannot take for granted that the quantile has a special form. Okay, and now, and this is what I'm going to generalize in higher dimensions. How can you perform a sort of, in practice, an estimation or regression of your quantile function in the general case? What does this mean? So, from what we've seen before, we see there are actually two ways to do this. It's to start from this problem, okay, with this is mass transport, but with a mean independence additional condition, okay. And the second way, so this is, of course, here the fact that y is one-dimensional plays no role. So this is really what's going to be the starting point of what we're going to do in higher dimension. And another point of view, which is very specific to the 1D case, is to say, well, there is a sort of dual problem. Let me recall the dual problem that was here. So you see, it's t by t. You make an estimation. But in the end, from this family of ut, you want to recover uniformly distributed random variable u, such that, in fact, the ut is sort of a characteristic function of the level set of this u. So those guys should be nested. there should be some monotonicity in the UT. So one way to perform quantile regression globally, I mean not T by T, but globally, is to maximize this integral. We've got the same moment condition as before, but you have the global constraint that the UT should be non-increasing with respect to T. Okay? So you see, in general, you could solve this problem. You can, this is another problem, and in fact, I'm not going to get into this because I don't really have time, but it turns out that those two sort of variants of quantile regression or generalization of quantile regressions are in fact equivalent. Okay, those two approaches are the same, but this one, of course, makes no sense in higher dimension. Okay, so let me. Is it clear so far? Okay, I don't know, but no, this one does. And this one, not really, because the order plays a role. Okay? Okay, so now let me recall a little bit of optimal transport. So the first question is, how do you define a quantile in several dimensions? And of course, there's no single answer to a problem like this. But one way to do this is by optimal transport, using instead, and to have the point of view that, well, quantile in several dimensions, maybe a reasonable way to define them is through optimal transport. Okay? So the optimal transport problem with the simplest case, with the quadratic cost or the maximizing the covariance, it's exactly the same, is to say, well, I have my y, it is fixed. I look for a random variable v, which is, I prescribe the law, it's uniform on a cube, let's say. Prescribed. It could be another, if you prefer a Gaussian, there's no big deal about it. And you want to look at the one which is maximally correlated to y. This is the same as minimizing the squared mean distance. Okay? And now there's a nice, very nice result of, very classical by now, result of Jan Brenier in the late 80s, beginning of the 90s, which says that this problem essentially as a unique solution, which is given by a map, which is characterized as being the gradient of a convex function. And gradients of convex functions are monotone in some sense. We saw this morning again with Walter Stolk. And, well, you could say, well, quantile function in several dimensions, maybe a way to do this is by solving an optimal transport problem. And this gives rise to gradient of convex function as a generalization. It's not the only one, of course, as a generalization of monotonicity. Okay? So, with this point of view, you will say that the grad phi, which solves the optimal transport problem, is really the quantile, and you've got polar factorization or pointwise relation that your y can be written as grad phi of u. U, the law is fixed, it's uniform on the cube, and this map is monotone, and it's a gradient. Okay, that's what really Brenier had fluid mechanics problem in mind when he proved a theorem like this. He said, well, the u is the rotation part of the y, and the grad phi is the compression part. It's any vector field can be decomposed in a canonical way as a compression part and a rotation part. Okay. So, okay, now let's go to the conditional setting. So, not only you have y, but you have also x, and you want to somehow explain the conditional quantile of y given x. So conditional quantile is exactly the same. What you do, you look at the disintegration or the conditional measure of y given x. You denote it nu x. You perform this optimal transport from the unit, the uniform measure on the cube to this conditional measure nu x. You end up with the gradient of a convex function, which depends on x, but as a function of u, it's a gradient, it's a monotone in the multi-dimensional setting. And you will call this map the conditional quantile of y given x. Okay? So now, with this point of view, everything more or less works exactly as in the unidimensional setting. Under some regularity, morally, you can invert the quantile. It's just what Legendre-Fenchel duality does. You can write u or y as q of xu. Okay, still have the pointwise relation, and of course, again, the conditional quantile is a random variable. The u, sorry, that you get in this decomposition is uniformly distributed, and it's actually also independent from y, and it maximizes the correlation again. Okay. And oh, okay. So I realized, okay, there are two things which are bad with this slide. The first one is that this comment should not be here because it's not. There's no obvious link with the martingale transport. And I realized during this conference that now I should expand this list of authors a lot, right? But sorry. Okay. So now in practice, you would like to estimate the conditional quantiles. You'd like, again, a linear form, an affine form. So you're looking for a relation of this type, alpha u plus beta u x. So alpha now is a vector, and beta is a matrix. But you want this guy also to be a gradient with respect to u. So alpha, in fact, should be a gradient of some map. So instead of having several degrees of freedom, it only has one. And beta should be a Jacobian, or transpose of a Jacobian matrix. And also to be consistent with what a quantile is, which is here in the gradient of a convex function, you should also have that this map as a function of u should be convex. Okay? So again, if you are lucky enough, if the true model for the joint law of xy is such that all those assumptions are true, the quantile has this form with a guy like this which is convex, okay, then you can do this sort of linear regression, okay, with this is linear in x, but this is the gradient of a convex function of y, of u, sorry. But now you can ask yourself, and of course it minimizes, it maximizes the correlation with a mean independence condition. Okay, so I will say, oh, sorry, I was not precise at that point. You can weaken a little bit. Specification is u should be independent from x, and quasi-specification is you solve, is you got this relation, but you weaken independence into mean independence. But now the starting point, the question is, look at this problem, which looks a little bit like the martingale optimal transport problem, because on top of marginal constraints, you add conditional constraints on your joint law. Look at this problem and look for optimality conditions and ask yourself if you are really, how is it linked to quantile regression? Does it say something in practice useful for having an estimation of the quantile of y given x? Okay, so now, from now on, I'm going to focus on this problem, the conditional, the mean independent optimal transport problem. And, okay, this is a question. Start from this and ask yourself if the output of solving a problem like this has something to do with quantile regression. And as usual, a good starting point is duality theory. So I'm not going to get too much into this, but you can, of course, rephrase this problem formulated in terms of random variables, in terms of a linear programming problem, in terms of joint law. So you look for a joint law for x, y, u, theta, where the marginals are fixed. So the xy marginal is the law of nu, is the law of xy. It's nu, it's prescribed. The law, the projection on the u variable is uniform on the cube. And what you add also is the mean independence condition. So the mean independence condition can be dualized this way. It just says that when you take a linear function of x with a coefficient which only depends on u, the output should be 0. Okay? And the marginal constraints can be dualized as usual, just by integrating by function only on the u variable or the xy variable. And when you see this, it's not very difficult. It's what you do is to transform a problem like this with constraint in soup in form, and you write in Lagrangian form the mean independence optimality problem, and you write it in soup in form, and the dual, I'm being very formal, is the inf soup problem, where, but you're all familiar, I think, with all those manipulations from for duality for convex or linear programming. You end up with the problem of finding two potentials, psi and phi, which satisfy pointwise this relation. So this is a term which adds to take into account the mean independence problem, exactly as what we've seen. Well, it was more an y minus x, an increment in the martingale transport problem. Okay? So first remark is that it's not totally obvious that there should exist optimal potential for a problem like this. In the unconstrained problem, it's very clear you don't have this term. The B, you don't know the B. B is zero, basically, in the optimal transport problem, Brognier, for instance. And in fact, psi and phi then are convex conjugate functions. They have a lot of regularity. You've got a lot of rigidity in the set of convex functions, and this gives you enough compactness to find a minimizer to this dual problem. So here, what I'm stating, and I'm going to use this to go back to the econometric motivation of my talk, what we can prove under some assumptions, which are probably not optimal, but at least in practice it's not so bad. So under some regularity assumption on the marginals, what you can prove is that there exist optimal potentials, psi, phi, and b, the multiplier associated to the mean independence constraint, which in general, they have no regularity, but are no better than L1. And of course, and for this you don't need a bunch of assumptions, you've got duality. So the inf in the dual coincides with the soup in the primal, from which you don't need anything. Just mention, I'm not going to get into the proof. It's not so complicated, but the key point, and actually I heard that also in the talk of Marcel yesterday, the key point really is to use to have L1 bounds. You have to work a little bit with the geometry of the problem, and from that you get L1 bounds on the B and on the phi, and then you're done basically. You use Komlow's theorem, and from this you can find a minimizing sequence which converges almost everywhere, and then you're done. Okay, so let me now go back to what we want to do. What we want to do in statistics, we would like to write y as a function of u and x. U should be mean independent from x. This dependence should be linear with x. This is just a practical assumption. You don't have any dependence, but it's linear. It's the simplest you can think of. And this guy should be a gradient as a function of u and should be also monotone, okay? Because this is what you expect from a quantile. So do we do this by using this duality? In fact, not really, but not so far. The first observation is that the function psi can be written like this. So in fact, the psi is a good function. It's a convex function of x and y. Okay? It's a supremum of a fine function of y and x. So this is really a convex function. And optimality tells us, or duality relation tells us that x, y, u, the optimal couplings between our free variables, and the potentials are related. You've got an inequality pointwise, but you've got equality almost everywhere when you replace x and y by capital X, capital Y, and t by capital U. And this means, in particular, this means here that some guys live in the subgradients of psi, which is well defined. It's a convex function, right? So the duality relation tells us that minus bu u is in the subgradients of psi, or by duality, the same as saying that xy is in the subdifferential of psi star at minus bu u. Okay? This is not exactly what we want, But formally, it is okay. We can see that it is just a matter of smoothness and a matter of convexity. So, okay, let me go back to this, this formula. And when you replace y and x by capital Y and capital X, this should be maximized by t equals capital U of omega, okay? The same omega, that's what I mean. So it says that, in some sense, the gradient with respect to t at t equals u should be 0. And this gives you exactly this relation, right? Y is gradient phi of u plus dbu transpose x, which is the gradient with respect to u of a function which is linear with respect to x, okay? And if it turns out that this function is in fact convex with respect to u, okay, then you get exactly what you want to do by performing quantile regression. You got this pointwise relation, okay, and you got the good monisticity. Of course, this is not true because you don't have smoothness at all of the B, and you don't have convexity of this guy with respect to x. But what I want to show you now is that what you do by solving this, this optimal problem, this optimal transport problem, is just a sort of relaxation of what you want to do in quantile regression. Okay? So this is probably what's coming next. Okay. So we know that we've got optimal potential, psi, phi, and b. So define this function phi x, phi of x and u is phi of u plus b of u x. It's non-smooth, and it's not convex with respect to u. But there are some, but the function is related in some sense to the function psi, which is convex. So what you can, playing with extremality relation, what you get, in fact, is that this function phi x, okay, it's not convex, but almost everywhere it coincides with this convex convex envelope, okay, with respect to u. So almost everywhere, phi x u equals phi x double star of u. So it means, of course, what is nasty is the dependence of this guy. This guy is random, right? And second thing is that you would like y to be the gradient of phi x of u with phi x convex with respect to u. You don't have convexity, but almost, okay? Because almost everywhere phi x coincides with this convex envelope. And now it is true by optimality conditions that y is in the subgradient of this convex envelope with respect to u for fixed x. So what you are doing with this mass transport problem, you don't care about specification or quasi-specification. Quasi-specification or specification is you're lucky enough so that the phi x has good properties, right? It has some smoothness and it has some convexity properties. In general, it's not the case. But the optimality condition tell us that you're not far from that. You're really not far. Almost surely the phi x coincides with this convex envelope with respect to u, and the pointwise relation linking y, x, and u is almost satisfied. If you could replace phi x double star by phi x, you would have exactly what you want. Okay? And now I think it's a good start to, good point to start, to stop, sorry. When you come to the end, you're always happy, so, no, don't worry, I'm not going to start again. Of course, I didn't talk about, didn't give any details and so on, but you could change the cost, you can, and I think, but what's really important is to do numerics on this problem, right? It's really a problem that, I don't know in finance, but people in biometrics are really interested. For instance, let me take again the example of the health of a baby. It is typically multidimensional, right? You got the size, the age, the weight, the capacity of the lung, and so on. So it's typically a case where you would like to perform multidimensional quantile regressions. And here we've got linear programming problems, which are not so good, but not so bad neither. And in fact, it can be attacked by quite easily by linear programming techniques. Okay, so now I really stop. Thank you. Ah, it's a
Yeah, why can't you, instead of taking phi x, you just take phi x star star, the convex envelope, and you only work with this and forget about it?
Oh yeah, that's good. Yeah, but it is a result that's what you get by solving the optimal problem. Yeah, you're right. This is a message of my talk. Sorry, maybe I was not clear. Thanks for pointing this out. Yeah. What you do with optimal transport is that you make no assumption a priori, you do the same business, and what you get in the end is a phi x. If you're glad, if you're ready to pay the price of the 2 stars, well, it sounds nice. Okay, neither do I, but I'm glad that we agree on that. It's not so easy to convince people in statistics with this, right? You have to spend a lot of time. But but we agree on that. Where? Okay, because there are 2 potentials, the psi. But you fix the x, so it's partial subgradient. But I'm not using that, huh? Yeah. So psi is a nice potential. It's convex in both arguments. But the phi x is nasty. Is nasty for 2 reasons. It's nasty because of the dependence of the b, the Lagrange multiplier. It can really be wild. And it's not convex as a function of u, right? But what is nice is that it is linear with respect to x. Okay? So does it? Well, this is partial gradients. This is gradient with respect to the first variable. Okay, thank you.